This is an introduction to coating of tablets. My recommended reference for this material is Chapter 28, Coating of Tablets and Multiparticulate from your textbook Pharmaceutics, The Science of Dosage Form Design by Alton. First, what is tablet coating? Tablet coating is the application of a coating material to the exterior of a tablet with the intention of conferring benefits and properties to the dosage form over the uncoated variety. In its widest sense, the technology is also applicable to multiparticulate systems intended for modified release applications. To a much lesser extent, coating may also be applied to hard shell and soft elastic capsules. Types of coating include film coating, sugar coating, press coating. Of these, film coating is the major technique. Virtually all new coated products introduced to the market are film coated, while sugar coating is the most traditional technology and has seen no real developments in the recent years. It is still of some economic importance. Reasons for coating are varied. The major ones can be summarized in the following points. First, ingredients may need protection from the environment, particularly light and moisture. Second, many drugs have a bitter taste or otherwise unpleasant taste. Coating is an efficient way to mask such tastes. Also, tablets that are coated are somehow easier to swallow than uncoated tablets. Colored coating also masks any batch differences in the appearance of raw materials and hence allay patient concern over tablets differing appearance. It's important to keep in mind that reasons 2 and 3 are important to aid in patient compliance. Also, coating may be optimized with respect to coloration and gloss to aid in their sales appeal or to enforce a marketing brand identification. Colored coating aid in the rapid identification of a product by the manufacturer, the dispensing pharmacist, and the patient. Coating as well facilitates the handling of tablets on high-speed automatic filling and packaging equipment. Very often, coating confers an added mechanical strength to the tablet core. Cross-contamination is also reduced in the manufacturing process, as dusting from tablets is eliminated by coating. And the last very important reason is functional film coating are used to impart enteric or controlled release properties to the coated tablets, or more usually to coated multiparticulates. Press coating. The technology of press coating differs radically from film coating and sugar coating techniques. Press coating involves the compaction of a granular material around an already preformed core using compressing equipment similar to that used for the core itself. For example, Manicity dry coater is one of the equipment used to do so. Nowadays, press coating is used mainly to separate chemically incompatible materials, if one or more being placed in the core and the others in the coating layer. This will provide separation between these incompatible materials. However, if there is still an interference of contact left between the two layers, and this is expected, in such cases, where even this is important, then the process of a press coating can be taken one stage further. How? It is possible to apply 2 press coating layers to a tablet core using suitable equipment like Viscosity by Cota. This equipment produces press-coated tablets with perfect separation between active core and coatings, as the two can be separated by an inert middle layer. The formulation and the processing of the coating layer requires some care. Large or irregularly sized agglomerates of granules will cause the core to tilt in the second die, used for compression of the coating. Thus, there is the possibility of an incomplete coating with the core being visible at the tablet surface. The disadvantages of the process arise from the relative complexities of the mechanisms used in the compressing equipment. Now, sugar coating. It is maybe considered the traditional method of tablet coating. By definition, it involves the successive application of sucrose-based solutions to tablet cores in a suitable coating equipment. Conventional panning equipment with manual application of syrup has been extensively used, although more specialized equipment and automated methods are now making an impact on the process. Sugar coating is rarely used nowadays. For new products, most of the sugar-coated products are old products, and film coating is mainly used nowadays. The reasons beyond that are: sugar coating is time consuming. It takes from few hours to few days. The sugar coats are very thick comparing to film coating. More accidental toxicity can happen by children with sugar-coated tablets. Sugar coating does not offer modified release formulations, only for immediate release to mask the taste and aroma. The sugar coating process involves several steps, the duration of which ranges from few hours to few days. A successful product greatly depends on the skills of the coating operator. This is especially true in the pan ladling method, in which the coating solutions are poured over tablet cores. The operator determines the quantity of solution to add, the method and the rate of pouring, when to apply drying air, and how long or how fast the tablet should be tumbled in the pan. Newer techniques utilize spraying systems and varying degrees of automation to improve coating efficiency and product uniformity. Regardless of the method used, a successful sugar coating process yields elegant, highly glossed tablets. The tablet cores preferably have deep convex surfaces with thin rounded edges to facilitate sugar coating. Since sugar coating tends to be long and vigorous, the cores should be also relatively resistant to breakage, chipping, and abrasion. Sugar coating, as we said, is a multi-stage process and can be divided into the following steps or stages: sealing of the tablet cores, subcoating, smoothing or syruping, coloring or finishing, polishing, and we can add printing. Besides the description you have in your student manual, I'll add some notes to each stage. Sealing. Initially, the tablet cores to be sugar coated are sealed against the entry of water by application of a water impermeable polymer. Shellac has traditionally been used for this purpose and is indeed still used to a great deal today, although more reliable materials such as cellulose acetate phthalate CAP and polyvinyl acetate phthalate PVAP find favor. Subcoating stage. To attain the typically rounded profile of sugar-coated tablet, the sealed tablet core must be built up to gain the desired profile. This process of subcoating is usually performed by adding bulking agents such as calcium carbonate or talc to the applied sucrose solution. A gum like Acacia is also added to the applied suspension to act as a binder. Smoothing or syruping. As smoothing of the rest surfaces is done using syrups. After the correct profile has been obtained, the subcoated tablets will almost certainly have a rough surface, which have to be made smooth before the next stage. This is accomplished by the application of few coats of sucrose syrup. Coloring or finishing. Nearly all sugar-coated tablets are colored, as aesthetic appearance is usually considered to be of great importance with this dosage form. The pigments used are those and only those permitted by the national legislation of the country where products are to be marketed. Polishing stage. After the color coating stage, the tablets will require a separate polishing stage for them to acquire an acceptable appearance. Several methods can be used, but commonly beeswax and carnauba wax are in use. Printing. To facilitate identification, sugar-coated tablets are usually printed with a manufacturer's logo or code. The use of indented monograms for this purpose, as for film-coated tablets, would not be feasible as the considerable thickness of sugar coating would obliterate any core markings. The printing process used is an offset gravure in conjunction with special edible inks, although the inkjet process is starting to make impact. Typically, tablets are sugar-coated by a panning technique. The simplest form would be a traditional sugar coating pan with a supply of drying air, preferably of variable temperature and thermostatically controlled, and a fan-assisted extract to remove the dust and moisture-laden air. Methods of applying the coating syrup include manually using a ladle, and automatic control is available for the application of coating syrups. In general, the equipment listed under film coating can, with suitable modification, be used for sugar coating technique. Ideally, a sugar-coated tablet must comply with finished product specifications and any appropriate compendial requirements. Sugar-coated tablets should ideally be of a perfectly smooth rounded contour with even color coverage. Most manufacturers take advantage of the aesthetic appeal of sugar-coated tablet and polish to a high gloss. Any printing should be distinct with no smudging or broken print. In sugar coating, coating faults are usually associated with process defects such as splitting of the coat on storage caused by inadequate drying during the coating application. Here are some questions for you to answer. Please use your student manual to answer. All answers are there. Film coating. Probably this is the most modern and generally used technology in the tablet coating. Nearly all newly launched coated products are film coated for the reasons given in the table in your student manual. Film coating involves the deposition, usually by a spray method, of a thin film of polymer surrounding the tablet core. It is possible to use conventional panning equipment, as we will do in our practical session, but more usually specialized equipment is employed to take advantage of the fast coating times and high degree of automation as much as possible. The coating liquid, solution or suspension contains a polymer in a suitable liquid medium together with other ingredients such as pigments and plasticizers. This liquid sprayed onto a rotating mixed tablet bed or fluid bed. The drying conditions permit the removal of the solvent so as to leave a thin deposition of coating material around each tablet core. Film coating liquid typically comprises polymer or film former, plasticizer, glidant, opacifier, colorants, and solvents or liquid vehicle. Ideal characteristics of a film coating polymer. First, solubility. For conventional film coating, the polymer should have good solubility in aqueous fluids to facilitate the dissolution of the active ingredient from the finished dosage form. However, where a modified release action is required, the polymer system of low water solubility or permeability will be chosen. Viscosity. In general, polymers should have a low viscosity for a given concentration. This will permit the easy trouble-free spraying of their solution in industrial film coating equipment. Permeability. Film coating can be used to optimize the shelf life of a tablet preparation, as some polymers are efficient barriers against the permeability of water vapor or other atmospheric gases. These properties we mentioned vary widely between the individual polymers. Mechanical strength or properties. The particular polymer chosen for a film coat formulation must be one with adequate strength to withstand the impact and abrasion encountered in normal handling. Insufficient coating strength will be demonstrated by the development of cracks and other imperfections in the coat. It should be mentioned that the polymer chosen must also comply with relevant regulatory and pharmacopoeial requirements current in the intended marketing area. Types of polymer available for film coating include cellulose derivatives. Most are substituted ether of cellulose. For example, hydroxypropyl methylcellulose, the polymer we will use during our practical session, is the most widely used cellulosic polymer. Why? Because it is soluble in aqueous media, forms films that are mechanically tough, relatively easy to apply, and the resultant film can be clear or colored. Other cellulosic derivatives include methylcellulose and hydroxypropyl cellulose, as well as ethyl cellulose. Methacrylate AminoEster Copolymers. Basically, these polymers are insoluble in water below pH 4, but in a neutral or alkaline media, the film achieves solubility by swelling and increased permeability. For simple formulation, the disintegration of the coating can be optimized by the incorporation of water-soluble materials and also by starches. For coating designed to confer a modified release aspect to the final dosage form, more water-insoluble polymers are used. These include ethyl cellulose and amino-methacrylate copolymers. Yet, another group of polymers is designed to provide an enteric protection to the dosage form. This effect is achieved by the pH selectivity of the polymer, where it is insoluble at the low pH environment of the stomach, yet becomes soluble as the higher pH of the duodenum and the distal portion of the gastrointestinal system is reached. Plasticizers. Plasticizers are generally added to film coating formulation to modify the physical properties of the polymer to make it more usable. How? Via reducing the glass transition temperature, Tg, of the film former. Tg is the temperature below which the polymer is hard and brittle, glassy in general, and above which the polymer is elastic and rubbery. Plasticizers improve the formation and continuity of the film during coating. One important property is their ability to decrease film brittleness. As we said, it is generally accepted that the mechanism by which plasticizers exert their action is for them to interpose themselves on a molecular scale between the polymer strands. In doing so, they permit these strands to move more freely and allow the polymer to act in a more pliable fashion. Example on plasticizers include polyols, such as polyethylene glycol 400. Generally speaking, low molecular PEGs are used. Organic esters such as diethyl phthalate and oil or glycerides such as fractionated coconut oil and glycerine. In general, only water-miscible plasticizers can be used for aqueous-based spray systems. Colorants. Any permitted colorants in a film coat formula are invariably water-soluble colors. Pigments. Pigments have certain advantages over water-soluble colors. First, They tend to be more chemically stable toward light, also provide better opacity and covering power, and optimize the impermeability of a given film to water vapor. Examples on colorants include iron oxide pigments, titanium dioxide, aluminum lakes. Other coating liquid ingredients are glidant, which is used to reduce the sticking of tablets during coating to each other and to the wall of the pan. Examples on these are talc. Opacifiers, these used to give chalky appearance or white background for the film. Thus, it improves the color coverage and intensity. Example on these is titanium dioxide. Solvents. It is worth mentioning that after the early development of film coating in the 1950s, the polymers used were invariably dissolved in an organic solvent. Modern technique now rely on water as a solvent because of the significant drawbacks that really became apparent with the use of organic solvents. These include the environmental effect, the safety precautions, the financial cost, and solvent residues. The vast majority of film-coated tablets are produced by a process which involves the atomization, spraying of the coating solution onto a bed of tablets, as we mentioned. Examples on equipment suitable for film coating include Acacia coater, high coater, and dryer coater. Fluidized bed principle is also utilized. In your manual, you will see a figure that shows probably the most widely used piece of equipment for film coating, which is Acacia coater. Here are some fundamental requirements that are more or less independent of the actual type of equipment being used for film coating. These include adequate means of atomizing the spray liquid for application to the tablet cores, adequate mixing and agitation of the tablet bed. Spray coating relies upon each core passing through the area of spraying. This is distinct from sugar coating, where each application is spread from tablet to tablet prior to drying. Sufficient heat input in the form of drying air to provide the latent heat of evaporation of the solvent. This is particularly important with aqueous-based spraying. And finally, good exhaust facilities to remove dust and solvent-laden air. Ideally, film-coated tablets should display an even coverage of film and color, and there should be no abrasion of the tablet edges or crowns. Also, logos and the break lines should be distinct and not filled in. And finally, the tablet must also be compliant with the finished product specifications and any relevant compendial requirements. Coating faults in film coating arise from two distinct causes. These are processing and formulation. In processing, for example, inadequate drying conditions will permit coating previously deposited on the tablet surface to stick against neighboring tablets. When parted, this will reveal the original core surface underneath. While in formulation coating faults, film cracking or bridging of break lines are examples. After taking due account of the mechanical properties of the film, reformulation will almost certainly be successful in overcoming the problem. As we mentioned, one of the most important reasons to coat is functional coating. Controlled release coating. Film coating provides an extremely effective way of conferring a controlled release aspect to a tablet or more usually a multi-particulate system. After coating, these particles are filled into hard gelatin shells or occasionally compressed directly into tablets by a process which permits minimal rupture of the applied film. The coatings involved use polymers with restricted water solubility or permeability and include methylcellulose and modified acrylate derivatives. Multiparticulates, commonly referred to as pellets or beads, find favor over conventional non-disintegrating tablets for controlled release use. Enteric coating. This technique is used to protect the tablet core from disintegration in the acid environment of the stomach for one or more of the following reasons. First, prevention of acid attack on active constituents unstable at low pH. For example, PPIs, proton pump inhibitors. Second, to protect the stomach from the irritant effect of certain drugs. For example, NSAIDs. To facilitate absorption of a drug that is preferentially absorbed distal to the stomach, or to target the site of action. Sulfasalazine, used to treat inflammatory bowel syndromes, are example on these. Polymers commonly used for this purpose, enteric coating, include cellulose acetate phthalate. The pH of solubility is 5.2. Polyvinyl acetate phthalate and suitable acrylic derivatives. Because they possess free carboxylic acid groups on the backbone, they exhibit a differential pH solubility profile. Simply weak acids. They are almost insoluble in aqueous media at low pH, but as the pH rises, they experience a sharp, well-defined increase in the solubility at a specific pH. Enteric coating is possible using both sugar and film coating techniques, but no one is using sugar coating for this purpose. But enteric film coating. Here we can use all polymers we mentioned. These are capable of forming a direct film in film coating process, but sufficient weights of enteric polymer must be used to ensure an efficient enteric effect. This is normally 2 or 3 times the required for simple film coating. Enteric sugar coating. The sealing coat is modified to comprise one of the enteric polymers in sufficient quantity to pass the enteric test for disintegration. The subcoating and subsequent coating steps are then as for conventional sugar coating, but again, no one is using sugar coating for enteric coating in real life. Here are some problems for you to practice the calculations that will be discussed for aqueous film coating experiment and the solution of enteric coated tablet. Thank you all.